or the previous. So what we're doing was trying to, you recall there was this partitioning estimator that we introduced, which said that this is within the class of local averaging. So instead of doing like k-nearest neighbors or some other variance like the Nadario-Watson, what we were doing was just partition the space, like the X space, and then average within each cell of the partition. Okay, so average the Y's within each cell of the partition that your test point lands in. So if you have a point X that lands in this piece of this partition or this piece of the partition, you go look at all the training examples Xi that are in that partition, and then you average their Y's. And that would be a regression function. If you're doing classification, because you're going to compare with 1/2, it's equivalent to like taking the majority vote among the Y's that are associated with those points. Okay, so it's a very simple estimator. Is very similar to doing histograms. So you know how to do histograms for estimating the distribution. This is like doing histogram essentially on Y's to determine the estimator. And so we wanted to understand, basically the point was trying to understand this bias variance trade-off that happens as you vary the bandwidth. So if you remove, this was the Nadario-Watson with the Gaussian kernel. So it has this interesting feature that when you vary the bandwidth, there's an optimal choice of the bandwidth. Too low or too high is gonna not be good. So and then we saw that this effect is not as amplified for classification, because the classification cares about the boundary, and you could do a lot of crazy things outside and still do good near the boundary. So in order to understand that, and also to talk about regression, which is what a statistician really like, we introduced this idea that we can look at any like prediction problem, not necessarily classification, but just going back to the basic idea of defining a loss function, a risk function, trying to minimize. So in the case of the regression, usually your response is real value, but this framework later you can generalize in like any type of response that you try to predict. So far we have seen binary and real value, but you can think of vectors or some like other things if you want to try to predict. But for this, the natural loss is quadratic, or at least like traditional classical loss. And then the risk is the expectation of this loss, which is called the MSE. And then we had the optimal rule, which minimizes the posterior risk. And we did the calculation. It turns out that the solution of this is exactly the regression function, which is the posterior mean of Y given X. And then, as I mentioned, all the estimators for this eta that we had in the context of classification, if you go through, there are good estimators, even if Y is not binary. So for example, this partitioning estimator that we had for the regression estimator is really a good estimate of this eta function. Eta might not go from 0 to 1 in general, but the same idea applies to regression. So what I wanted to do now is to analyze the MSE of this partitioning estimator in the regression context and see how this bias variance trade-off works out. And it gives you a lot of intuition of what exactly is like controlling this prediction problem. Okay, just to recap again, we did some preliminary calculation and showed that this risk, which is the like basically for any function, basically it's the difference of Y and your prediction of Y, which is Y hat, which is f of X for any F. I did conditioning on X, the test point, and then we showed that this prediction error basically at point X, like a fixed test point, and can be decomposed into this part and a part which is exactly the same conditional risk, but for the eta, which is the true, like the Bayes rule or the optimal rule. So this part cannot be improved. This is the variance of Y given X. There is an unimprovable part, so you can't do perfect prediction if there is noise in your problem, and this is capturing that. So this part I can improve. There is going to be a regression function, whether I know it or not, it's there. That's the conditional expectation of y given x, and there is a difference between y. So that's the conditional variance of y given x, and that is out of my control. Once I set up the problem, once y and x are determined, this is determined. This is like unimprovable, or the Bayes risk, if you want, the conditional Bayes risk, conditional on x. This part I can improve basically by taking f to be equal to eta of x. That also proves that basically eta of x is optimal. But I don't know eta of x, so this is not going to be in practice going to 0, but I can aim to get this close to 0. And just to introduce a notation, the difference of this risk minus the minimum is sometimes called the excess risk. So this part is the excess risk. So the excess risk I can drive to 0 eventually. But the original risk is there's going to be a minimum value. Just like classification, that when you compute the risk of the Bayes rule or the optimal rule, it's not necessarily 0. So in your like the example that you did, the exponential case, it was like 0.38 or something like that. So we're going to focus on this excess risk. This would be like conditional excess risk. Conditional here is I'm conditioning on a particular test point. And so to analyze this, we're going to analyze it for this eta hat, which is our partitioning estimator. So I'm going to look at the difference of the partitioning estimator at a particular point relative to the true regression function squared. And then this is going to be a random variable. So in order to analyze it, it's simpler to just look at the average case. So what happens on average? And what I'm going to take the average on is conditional on the training examples. So I've introduced this notation, which is, you can ignore the tilde if you want. But what this is saying is that I'm looking at this conditional on x1 up to xn being fixed. These are the training x's. What I let vary is the y's of the training. So I assume that the training x's are fixed. I just let the y's vary. This is the easiest case that we can analyze, and you can, if you need later, you can try to pull back everything, state an unconditional result. But I think this captures this like the minimum amount that you can do to capture like the essence of the problem without complicating things. So what we're going to do now is remember this notation. We're going to have the variance as well. Variance tilde means variance conditional on the training x's, and so on. So what I'm going to study now is this conditional, the expectation, this with tilde of eta hat minus eta x squared, and see what happens. Okay, that's what we are going to do today. Okay, sounds good. Questions? So let me move with like an updated set of slides here. It's sort of the same thing. Yeah, so what I want to study is yeah, let me maybe point out. What I'm going to study here is expectation of eta hat x minus eta x squared. And this eta hat x is the sort of local averaging estimator. So if you remember, it's I from 1 to n. The way we said it, like, or set up the notation, xi is an ax times yi, and then divided by summation I from 1 to n, xi in ax. So ax is the cell of the partition that contains the cell that contains, okay, not the partition, the cell of the partition in which x lands. This is probably less ambiguous. So I would have like the partition here. Usually, like, doesn't have to be uniformly like equal or equispaced, but for simplicity, let's assume like we are in 0, 1, for example, and then this is like length is h, and what I happen to have like is x, this would be like a of x. So this interval, right? If x is in there, then a of x is that partition. And I'm going to look at all the, basically this indicator is telling us that look at all the xi's that are within that partition, all the like little training data points that are there, and then look at all the y's. So some of them are 1, some of them are 0. So for example, one of these would be like 1, the other one would be 0, another one would be 0, another one would be 1. So I'm going to look at this and then just average over all the y's. So in this case, if like suppose there are 4, 2 of them are 1, 2 of them are 0. That would be like basically for 2 of them, this would be so this would be basically 4. There are 4 points, and out of those, this is going to be just 2, for example, because 2 of them are 1. So you get 1 half. Right, this counts how many points land in there. That counts how many points land in there, and yi is 1. Sorry, yeah, so okay, so we're not looking at, this is going to be 4, but we're looking at the general regression. So yi is not necessarily, it's not necessarily 0 or 1, so it could be different values. So basically, this is going to be the average of yi's that for x's that land there. Okay, so they're going to be 4, and those 4 would have some values. Let me maybe do a better job here. This would be maybe 3. Let's say 1/3, 2/3, 1. Let's say h here would be 1/3, and then this is ax. X would be, for example, here. That's x, and then my points would be, for example, like one would be here, the other would be there, that would be there. So I'm just going to take these points, the x's like x1, not that one, but these are the xi's that are there, and then I just average the yi's. So that would be my value of the regression function. It would be like constant here. So for any x that is there, it's just going to be the average of these, which is going to be something like that. In another sort of interval, it's going to be the average of everything that's there. So it's going to be another constant there, and so on. So for all the x's, our regression function would be constant. It's just the average of the training data points that are there. Okay. Is the idea clear? So what I'm going to introduce is this notation that counts nu n of A, which is going to count, it's actually basically average. How many of these xi's are in a set A? This is a generic, this is sometimes called the empirical measure of the training data. So this, for any set A, for any interval or any set A, it counts how many, like the proportion of the xi's that land in there, okay? How many there are divided by the total number. So this is called the empirical measure for the distribution of xi. And so if I have that, then I can write this as, if I multiply by 1/n, both sides, the denominator would be nu n of ax. So this is like the fraction of points that land in ax. The numerator would be basically summation I from 1 to n, 1/n indicator xi in ax times yi. This is going to be simpler for us. So that's an alternative representation of eta hat x. Okay, just a notation. This just, for example, counts, let's say the total, there are like 10 data points total. There are 4 of them in this, so it would be like 4/10. This would be 4/10. Yeah, just a fraction, not the count. And this object has a lot of interesting properties. It's like a probability measure, probability distribution. In any case, okay, so that's some notation. Is it clear? So the estimator that you're analyzing, partitioning estimator, I just rewrote it in terms of this notation, new notation. It helps us with the analysis. And then you can also think of this as if we go one step further, you have seen it before, I can write eta hat x as just summation I from 1 to n, wi x yi. There's some weight. This weight turns out to be just 1 over n summation, sorry, not summation, indicator xi ax divided by mu n ex. Okay, so that's, oh, sorry. That's just, like combining this and that. So this part does not depend on I move it inside. And so now I have this weight. So this weight is multiplying that. So you have seen these formulas before. It's just another convenient way of writing things. Okay, so we are weighting and the weights are these. Okay. Just a bunch of notations for now. Any questions? Maybe zoom out. You guys can stare at it a little bit. Questions? Yes.
We don't need the 1 over n though, right? So it's cancel out.
Cancels out, but introduce it for a reason. Cancels out, but let's have it there. So just deliberately like multiplied by 1 over n. This is the way that mu n is defined if there's a 1 over n there. But instead of counting, I'm like looking at the proportion. These are equivalent. You'll see why I did that. Very short. In order to calculate this, you don't need it, but it's easier for analysis. Any other questions? Yeah.
What's the words before at the end of the empirical measure?
Oh, for the distribution of xi. For the, like, let's call it marginal. Let's say marginal. Okay, it's better to say this empirical measure for the marginal distribution of x, a generic x, based on the training data. So remember, we had like a generic xy from a joint distribution P. Under this joint distribution, x will have a marginal distribution. For example, we had like x conditional on y. You remember the case that we did like exponential 2 minus y, that was your exercise. And then we had y is like Bernoulli 1/2. From these, you get them like x has a certain distribution. Like you can write the densities. Right, so that's the marginal distribution. I can estimate the marginal distribution by this guy. And this is like the empirical version. Given any a, basically, you can tell me what this is like going to approximate that marginal distribution has a x has a marginal distribution under this model. What I'm saying is that it's not the joint distribution with y, it's just based on xi, so it's a marginal distribution of x. Okay, sounds good. We haven't really done anything except introducing some notation and like getting ourselves familiar with this partitioning estimator. Now what I want to do is, any other questions? Do the calculation. So I want to estimate or calculate expectation tilde of eta hat x minus eta x squared. Okay, the first thing that we know is this is like another MSE type thing. So expectation of something is squared, some error is squared. The MSE always has a decomposition. This has a decomposition like this. I can add and subtract the mean of eta hat. So add this in here. And then this is one of your exercises. You expand and then you show that this reduces to expectation of eta hat x minus eta x, the first term, squared plus the second term. This guy is squared, there's a cross term that goes away. So this is going to be the variance of eta hat. I'm not going to go into details because that's your exercise. But in the end, what happens is that you have variance of eta hat x plus this term, which is called the bias squared. So every MSE that you write has this bias. This is going to be like variance plus bias squared. So MSE can be written as this. So that's our MSE. So there's this variance plus bias squared. This is certainly the variance. This is the expectation of eta hat minus the quantity that you want to estimate. So the expectation of your estimator minus the quantity of interest, that's the bias of the estimator. So it's going to be unbiased if this term is 0. We'll see that it's not necessarily unbiased. But there's this bias squared. So has anyone seen this bias variance decomposition before? Seen it? Okay, you're gonna prove it in your homework exam exercise to make sure that you've seen it. But the basic idea is just add and subtract the expectation of eta hat. And then it's very similar to what we did last time when we tried to decompose the prediction error, if you recall. There's going to be cross term that you argue that vanishes, but basically I did half of it for you. The rest you do. So that's one idea. So in order to study that quantity, which is sort of the conditional MSE, I just have to study the variance of the hat. And I'm going to put a hat here, a tilde here, because these are all expectations and variance is under the conditioning on the training axis. You can ignore the tildes there. I'm going to study so what I need to study is this variance and this guy. Separate. So the variance is easy, the bias is harder, usually. Analyzing the bias is hard. So any questions so far? Okay, so let's try to control the variance. So that's the notation. So maybe I'll leave it here if you guys want to write it down. Any questions? Okay, that's what I said before. That's like our notation for the empirical distribution. These are the weights here. That's the notation for that. And this is the MSE is equal to bias squared plus variance. Okay, now I want to control the bias and the variance, and that's another exercise for you guys. So we know that eta hat x is summation I from 1 to n wix yi, and my claim is that the expectation of this, when I take the expectation, this turns out to be summation I from 1 to n wix, because this does not depend on, this only depends on the xi, if you remember. So wix is 1 over n indicator xi in ax divided by nu n ax. So nu n and everything here depends on xi, and I'm conditioning on the training xi. So this is going to be constant. So this can come out. And the expectation of this guy is going to be eta x. That's, sorry, eta xi. This is what I want you to show. That's this part. So the expectation of this would be these weights and then multiplied by the true regression function evaluated at the training data points. Just maybe ask you a question towards your homework problem. How do you show something like this? Let me do it down here. I'm going to help you guys. So if you take the expectation, because Wix is constant and the expectation is linear, it's going to move past. So you can argue that this is going to be Yi like this. And then you want to argue that this is the same as eta of xi. I'll let you argue this for yourself. Eta is basically, remember, eta is conditional. This is conditional expectation of a generic y given x is equal to x. And this is, there is some sort of a condition here. So this is really expectation of yi conditional x1 up to xn. What we're claiming is that this turns out to be equal to eta of xi. So the expectation is these weights times eta evaluated xi. I'll let you figure out the details. Also for the variance, if I look at the guy here, the variance of eta at x is going to be the variance of tilde again of this. I have a sum of a bunch of independent weighted sum of a bunch of independent variables. How do you calculate the variance of sum of independent variables? Okay, because they are independent, the summation comes out. Okay, it's constant because you're conditioning on the x's. So this comes out as squared, right? Variance tilde of yi. And here I'm going to assume, I'm assuming that the conditional variance of y given a generic x, this is in the generic setting. This is sigma squared. That's what we're going to assume. It's not needed, but it's simplified. So the conditional variance of y given x is sigma squared. And then what you're going to argue for yourself in your homework problem, this is really sigma squared. Okay, because this is yi conditional on everything, but sort of argue that's basically variance of yi conditional really in xi, because the rest are independent. So if you believe that, then what we get is sigma squared. That's the first half. The second half is I'm just multiplying. If you think about this, right? Sigma squared summation wi squared x, right? I from 1 to n. These wi's are like this. And so I'll let you do the calculation because of this form. Once you do the calculation, it turns out that this is equal to, you can write it like this, sigma squared over n times 1 over like nu n ax. This is like an algebra using that. I'm going to let you figure it out. So there's a bit of like the statistics here that the expectation of linear goes in the variance of independent stuff. Like it's the variance of sum of independent variables is the sum of the variances. But do the calculations. So in the end, it turns out that the expectation is this and the variance is that. So what I want to like now do is like actually analyze these expressions. So you show these expressions, we already showed it sort of. But let's see what the consequence is. And then you figure out the details of this, okay? So I have calculated an expression for this here and an expression for this other guy. So this particular expression is really simple. And this we already showed here, if you sort of showed. And then you do the algebra, you get that. So let's analyze the variance. So maybe first ask you if you have any questions here. So the path is sort of clear how to do this. Okay, so what I want to do is calculate the these expressions for you guys. Cut. So let's see what the variance is. So controlling the variance. And it has a lot of interesting meaning. Controlling the variance. So that calculation shows that the variance of this partitioning estimator at point X is just sigma squared over n. Sigma squared over n should look familiar to you guys. This is like the how, for example, the variance of a sample mean goes down. If you're computing an average, there is this other term here, which is nu n of ax. And nu n of ax is just 1 over n summation I from 1 to n. Indicator. Xi is in ax. Okay. That's what the variance is. So now my question to you guys is, what happens as the sample size grows? What happens to this guy? That was a lucky non-guess, because that's not correct. It's not going to go to 0. Why would it go to 0? It's like an empirical average. What happens to empirical average as the sample size grows? Approximates the population. So what would be the population here? So these are IID drawn from a distribution. So these are like Bernoulli variables, independent. They have the same sort of distribution. So there's a law of something, law of large numbers, that says that averages of IID variables converge to the expectation, right? Right. The expectation, and one of them is the probability. So it converges to the probability of one of them, let's say xi equal to ax. So this is the distribution that I mentioned is the marginal distribution. Sometimes I might write in the notes ax, like nu x. This is the marginal distribution for a generic data point. Okay, so this converges to the probability that a random x that you pick lands in the set ax. You have like a generic point xy from P. If I randomly pick x from this distribution, there is a probability that it lands in this. I'm just going to write it like that. It's easier. Like the generic x, the probability under that generic distribution that x lands in ax. So that's this probability. Sometimes I write it like that. It becomes clear that this is converging to a population quantity. So asymptotically, this is approximately going to be sigma squared over n times nu ax. So let's see what nu ax would be. If for simplicity, I'm going to assume that the distribution of x is uniform. So marginal distribution is uniform, let's say in 0 to 1. Okay, like example. Assume that the marginal distribution is uniform 0 to 1. The points that we draw for the training would be like uniform 0 to 1. And then the partitions, I have to specify what exactly the partition is and what the distribution of x is to figure out this. I'm going to assume the partition is equally spaced. So length h. And how many partition cells we'll have? We'll have like 1 over h cells. Okay, so if I draw uniformly from 0 to 1, if the marginal distribution is uniform 0 to 1, and if I look at one of these generic cells, what is just the chance that the generic x lands in that cell? You draw uniformly in 0 to 1. What is the probability that your x lands in one of these, like fixed one partition cell, each has length h, 1 over h. So this would be the probability of x landing in ax would be 1 over h regardless of, so ax. So ax depends on This is like a test point, right? It's going to change depending on test point, but it doesn't matter which one you pick. That probability doesn't depend on X. So that's why it simplifies. So it's actually not 1 over H. It's H itself. Can be 1 over H because it blows up if H is small. So H I can be at most. So 1 over H is the density. The probability that you land in this would be proportional or exactly equal to the length of this interval if you use it on the exam.
Oh, those deep stroke.
Yeah, 1 over H cells, H is the length of the cell. It's the bandwidth, right? Let's forget about this. So H is the length of the cell. So this would be sigma squared over n times H. So you can see the bandwidth, how it controls the variance. If the bandwidth gets smaller, the variance blows up. Intuitively, what happens is that it's harder to capture like training data sets in a cell. Once you make it small, the probability you get like a generic data point in there gets smaller. So when you do training, this is roughly how many n times this is how many. So you can see like n times nu n ax. This times that is exactly how many training data you see in that cell, and this is asymptotically close to n times nu ax, which we talked about here. So n times the probability, this would be asymptotically how many training data points you get. And so because you're averaging over those many data points, your variance would be sigma squared over this is roughly how many data points you're averaging over. And you can see the bandwidth controls that. The bandwidth controls this via the probability. So this n times H is roughly like asymptotically how many data points from training x1 up to xn land in AX. And you can see that it gets smaller. The number of data points gets smaller as you shrink H. So that causes your values to go up. So if H is large, there are a lot of training points. And then when you average, the variance goes down. If H is small, there are few, and you could be like just one. You're averaging over 1 or 2 data points when it goes up. So this has a lot of intuition behind it. And there's an exercise you can show that if it's not uniform, also the density comes in. So you can write it in terms of the density, marginal density also controls it. So in places where the marginal density of X puts less mass, because you're going to observe less number of points, your variance is going to go up. But this gives you a rough idea. Okay, so this is like order-wise, it's going to be sigma squared over n times H. And so the bandwidth sort of, so for variance, what bandwidths are better? I ask you guys. Wider would be better. You capture more points. I think what n times H is roughly the expected number of points that you get basically is what it is, asymptotically. The wider intervals are better. So in order to reduce the variance, you need bigger H. But that would like increase the bias, as we'll see. Any questions about this? So this takes care of one part of the MSE. Questions, comments? Okay, so let's do the bias. It's a little bit trickier. So eta hat x, I just have to worry about the expectation. So the bias is the expectation of this minus the true regression function. And that expectation has this form. So I'm going to just write that down. Summation I from 1 to n wix. The true regression function evaluated at xi. Okay. Let me cheat here a little bit. Let's see what I did there. So how do we analyze this? Okay, so let's do, yeah, so if you recall, this is really, I'm going to expand it again. So this notation was helpful for variance, but W is just, I'm going to expand 1 over n indicator xi in AX. That was the W divided by just new n AX. So recall that that was the W. Sorry. Copy. So if you just plug back in what this is, I'm going to plug it back here. For bias, it would be easier. So let's see what happens to the numerator first. I just plugged in WI. So numerator would be equal to 1 over n summation I from 1 to n indicator xi in AX. So times xi. So this is another empirical average. What does it converge to? So these are, again, variables, functions of xi, they're random variables. They're independent and they're IID because xi's are IID. It's like 1 over n summation some zi's if you want. So by the law of large numbers, this converges to expectation of like a generic one. Just going to write z. Z would be something like indicator a generic x in AX times eta of x. So if I want to write this, this would be an integral. So would be equal to an integral against the distribution of x. So it would be indicator x in AX. Okay, I'm going to write it as, yeah. It's a little bit hard. So I'm going to write it as u in AX. Okay, so let's for example, px be the density, the marginal density of the generic x. So this is going to converge. So it converges by the law of large numbers to expectation of z, which is integral that indicator. To avoid confusing with x, I'm going to use u. This eta u pu du. Okay, so this is a random variable. This is some function of x, right? Some f of xi, and this is just f of that u. So when you want to calculate the expectation, whatever that is, you integrate that function against the density of x. It's called the density px. So that would be px. This u is the dummy integral of the dummy integral. Does that make sense? It's just some function of xi. And if you have a generic function of xi, so you can write it as. So if you want to calculate the expectation of some function of xi, you integrate that function against the distribution of xi. The distribution of xi is just generic this, so you get something like that. I'm not using x because x is our test point here. It's going to be confusing. But that's sort of what it is. Hopefully you understand what this is. Then the denominator we already figured out denominator we already figured out, which is nu n ax. We know that this converges to the probability that x is in ax. That's what we had here, right? And this I can also write as an integral. It's just in the integral of, because this is also an expectation of indicator x in ax. Indicator x in ax, and then p x u. I'm going to put u here, eu. Okay, so this is another expectation of a random variable, and so it would be like that. This is just expectation of some function of x. I have to integrate that function against the density of x. Okay. So once the dust settles, this is going to converge. So what this is going to converge to, and I can simplify these a little bit. So because of the indicator, I can just say integral over just ax, pxu du. You already know this. So what is the probability that x is in ax? Just integrate the density over this. So this indicator is going to be always 0 except on that set. Similar thing happens here. This I can write as integral over ax, eta u, pxu du. I'll let you think about these, but the idea is simple. Okay, so this is just the probability that x lands in that set. The other one is just taking the averages of u with the density of x over that set. So what happens, the numerator goes to that, the denominator goes to this. So this guy copy. So this guy, the numerator is going to converge to that integral ax eta u px u du. The denominator is going to be like integral of pxu du ax. Okay. So you can think of this as a weighted average of the value of the actual regression function over this cell. And this is just, you want to write it another way. You can write it like this. Integral ax, eta u, and then pxu du divided by px, let's say u prime du prime. This is very much like the local averaging that we were doing. So this is like forget about the integral. This is, think of it as a sum. This is a weight. This is like sums over all those weights. So these weights are going to be normalized to be 1. If I remove this, the integral will be 1. Because if I integrate, the numerator will be the same. So this is like a weighted average. So these are weights, the weighted average of the values of eta over the set ax, the partition. And the weights are determined by like how the density varies. This is like the conditional density. This is like, can argue that this is just the probability that x belongs to, sorry, it's the density of, okay, so this is the density of x conditional on the fact that x belongs to ax. So given that ax lands in that set, what is the density? That would be the density, you can argue. But it doesn't matter. What I mean is just these sum to 1, and they're weighting this guy. So what happens is over this region, the regression function is going to vary over that cell of the partition. What our estimator, effectively the bias of the estimator, the expectation is doing is just averaging all these values with certain weights here that are these, and that would be the expectation. So that would be different from So the bias would be like this, minus this guy. So at any given point here, like x, eta x has a certain value, and the expectation of your estimator is going to be the average of this guy over that partition. It may not be, so it's going to be somewhere here, for example. It's not going to be exactly this value, but some other value, which is just the average of all values of eta, the true regression function. So because of the local averaging, the local averaging is applied to basically eta. So the true regression function is averaged over that cell of the partition, and it's going to, in general, differ from eta x. The only way that it's going to approach eta of x is what? What should happen for this average to approach eta of x at that particular value? So I'll give you a function, you average it over a set, and then there's a point in that set. There's no reason why the average of these values should be close to what the value of the function is at that point, except if something happens. One is that if the regression function is actually constant, if the regression function was truly constant in this region, when I average all the values match every value in the point. So that's the case. But if the regression function is varying, you're averaging out the values over AX, and what would happen? This turned out to be like looking harder than it is. It's really not hard. This calculation is not really hard. We can go over this at some point. But the point is that in the end, what you get is just this like averages of this over this set AX. The averages are the sort of density related to the conditional density of a generic data point landing in this. So there's like a density originally, now I condition on the fact that X is in there, it changes the shape of that density. So there's a mass here, and given those weights, I'm averaging this. You can think of this as being like uniform, because for the uniform cases, it's going to be uniform. So if the original density is uniform here, the density that we have here is going to be uniform. It will be uniform distribution on this. Okay, so for the uniform case, this is just going to be AX. This whole thing is just going to be 1 over AX. So this whole thing just simplifies. Probably I should have done this. I think it would have been much simpler. So what this turns out to be is this in the uniform case. So I'm just average like summing eta x and divide by the length of AX. Okay, so this is a sum values of eta x divided by the length of the interval. That's just the average. So that's equal to that. This is going to be constant. Very easy. In any case, this is only going to go to, I want this to go to eta x. In what condition would this go to eta x? The condition is that the length of this has to go to 0, because I'm averaging. The only way that in general this is going to go to this value is this if the length is shrinked. I have to shrink the length until the average is very close. Okay, so I'm averaging over an interval, and the only way that the average of the function is close to the value of the function. So this cell contains x. There's a cell that containing x. Averaging eta over that cell is going to, the average value is going to converge to the value at that point if the shell is shrinking towards that point. So the only way that happens is that length of the interval is getting smaller. So the bandwidth is getting smaller. So in order for this to converge, I need the bandwidth. So I need h to go to 0. Okay, that's how the bias is controlled. If you don't shrink the bandwidth to 0, then you're always going to be like estimating the regression function by this average value rather than the true point, at the true point. So you can't like reduce your bias. Even if your sample size grows, in the end, eventually as n grows to infinity, by the law of large number, this numerator converges to that, denominator converges to this, but this is still away from the actual eta x, because it's average of a bunch of things around it on that cell. The only way this average is going to go to zero, sorry, go to the central point is once you shrink the AX around this. So once you shrink it, which the length was h, remember? Once I shrink it, once I let h go to zero, this interval gets smaller and smaller. I'm averaging over smaller and smaller portions of eta x, eta, and then that would be. So the point was, you can't reduce the bias unless you let the bandwidth go to zero. Sounds good? It's more complicated than it looks. You said local averaging, we're doing local averaging on the training data in the population. It's like local averaging on the actual regression function. So you're averaging locally the regression function. The only way that that local average converges to the true value at that point is that that set that you're averaging over shrinks. Sounds good? Okay. So h has to go to zero for the bias to go to zero, but h has to go to infinity for the variance to go to zero, so you can see the trade-off. Okay, so if I assume more about the bias, you can actually get an estimate of how far this is. So this is the asymptotic expectation of your estimator. This is what you want. The difference is the bias, and you can control the bias, so you can find what this difference is. Because you guys are not looking great, I'm not going to do this, but there is, if I need to assume more. So for example, if I assume that h is continuous or smooth, then it's in the book, but let me show you, just give you the example. So there's a class of functions for which called the Lipschitz. So if eta is a Lipschitz, the technical term, so basically differentiable and the derivative doesn't vary fast. Then this is the difference is going to be bounded by LH. So not only you can say that it's going to zero, but you can also estimate the error between this and that. And you can see it's L is going to be constant time, it's going to be h. So the bias would be of the order of h, which is the length of the interval, which is not unreasonable. So in the end, let's say in this Lipschitz class, we had the MSE, which is eta at x minus eta x. This is like variance eta hat x plus the bias squared. So this approximately turned out, this one turned out to be sigma squared over NH. And this is going to be approximately, at least for the case where would be like LH squared, because the bias would be LH. So this roughly would be of this form, and you can see the variance goes down like 1 over h. The bias grows like h squared. And so if I plot this, you would see the effect. So if you plot this function, like fixed sigma squared in n and L, as h goes to 0, this blows up, this goes to 0, so you get go to infinity here. And as h goes to infinity, the first one goes to 0, the second one blows up, goes to infinity. So you have this curve, which is similar to what you observe in practice. So this is h, this is the MSE as a function of h. So in this regime, so variance blows up. Here the bias blows up. So there is a sweet spot, which is what you try to capture by cross-validation. Okay, in the context of regression, this would be very dramatic. In the context of classification, it's not. But there is this trade-off, and you can actually try to minimize here, and you get a value for h in terms of the n. So h has to grow at a certain rate in terms of n. So you can try to minimize something like this is not exact, but an approximate version of the MSE. I just wanted to point out this so that you see it's not really difficult. If we did this from the start for the uniform, which I should have done, this would be a lot simpler. But there's really nothing strange here. This converges to the expectation, this converges to the expectation. The expectations turns out to be like, for the denominator turns out to be actually this, for the numerator turns out to be this under the uniform assumption. And so And you can see that this, and you can control this for this Lipschitz class. In general, if you assume more about the regression function is smoother, this is going to go down faster. So it would be like h to some power, like 2 or 3 or 4. The smoother it is, the better your bias behaves. But you're not for the partitioning estimator, but if you use a more advanced estimator, you can reduce your bias further. So if it's like h to the 2, when you let h go to 0, this like goes down much faster because it gets squared and so on. But for the partitioning, you can do better than this. And so that's sort of the big picture. Okay. Questions? So some of the details you figure out. The details of this, I also like encourage you to go through for yourself, the controlling the bias. But the main point is that it's not going to help you if you like increase your sample size. You can reduce the variance, but the bias remains. The only way to reduce the bias is to shrink the bandwidth. So in practice, what happens if you do the calculation here, h would be, the optimal h would be n to some power that you can figure out from this, and n to the power of alpha. So your optimal bandwidth depends on the sample size. The more samples you gather, you can shrink the bandwidth more so that you balance out the bias and variance. So you can't keep your bandwidth fixed. If you keep it fixed, you're going to be, your MSE cannot. This is actually not, this is for us, is like the excess MSE. It's like excess beyond the Bayes rule. So the excess MSE, so you remember there's this part that we can't let, due to the noise variance, we can't shrink. But the part that we can shrink, the only way that can go to 0 is you let the bandwidth go to 0. And in practice, the optimal way to do it is to let it depend on n. So there's an exercise in the book. You look at this formula, this is a univariate function. Let's minimize this. And you can see it's going to be like a function of n. So we like, has to be, I don't know, n or to the third or something like that. It has to go down, but at the rate which depends on the smoothness class, which is this 2 here, and the sample size. So the more samples you get, you can shrink the edge faster so that eventually you both the bias and variance go to 0 at an optimal rate. Sounds good? Okay. Questions? Comments? Okay, so this is the main thing that I wanted to discuss, like from a theory perspective. I think this is good enough for now. You can do the exercise, like the homework problems, and you can like work this a little bit. So if you go through this argument, so this we did for like an interval. We did this for an interval. The variance was quite simple. If you go through the argument for a d-dimensional feature, suppose it's uniformly distributed on the d-dimensional cube, then when you do the calculation here, the probability is going to be h to the d rather than h. Let's say in the plane, it would be like h squared because the side lengths are like the area would be h squared. And so if you do the calculation for the, so for a d-dimensional feature, a d-dimensional. So the MSE as a function of h, the bias is not going to change, but the variance is going to be n times h to the d. So remember, this was like the number of like expected number of points that you capture in that region, and because the region would be like a little cube of sine like h in d-dimensional space, it would be h to the d. That's the area, like the volume. And this if you go through the argument that we did, the only thing that changes in this formula is this part, and you can see the variance gets worse as your dimension grows. So as you make the bandwidth small, this is going to blow up, right? So it used to be like 1 over h, now it's 1 over h to, let's say, 10. And this very quickly blows up, and it also shows you that in higher dimensions, it's harder to capture points like in a little interval, like cube. So less points fall into the cube as in higher, like lower dimensions. this is a manifestation of what they call carousel dimensionality. So if you're trying to do classification based on a feature which has like 60 elements, like we did it like with 1 or 2 features, but if you do with 60 elements, this would be h to the 60. So when I like shrink the bandwidth a little bit, this quickly like jumps. So if I like shrink it by 1/2, so change h to 1/2 h, then like you go from h to the d to like 1/h to the d to, so the variance would be, used to be like this. Now it's 2 to the d times 1/h. So if you have 10, for example, it would be 2 to the 10. It would be like increase it by a factor of 1,000. If you have 100 features, you increase it by a factor of 2 to the 100. Okay, so quickly, like the variance is hard, really hard. And if you try to make it small, then your bias would be very large. So that's the trade-off in high dimensions. If you don't assume much about the regression function, then there's this carousel dimensionality that kicks in. The expected number of points that you capture in a given interval. Okay, or at the volume. So you can play with these formulas. You get a lot of insights if you do that, and some of them I might assign more problems. But this is sort of the traditional picture of the bias variance trade-off. And you can see if you understand this, what exactly the role of the bandwidth here is. So if you make the bandwidth smaller, you're averaging over less number of points, so your variance goes up. If you increase the bandwidth, you're averaging the actual regression function over a larger region. So the fact that you're averaging, the average is going to be different from the actual value at that point, and that's the bias that you pay. So you have to sort of trade off these two things. Questions, comments? And this carousel dimensionality is quite like severe. And the reason, like we will see, like why like deep learning works, like everything like else works, is because you assume something about the regression function or something about the classification problem that avoids doing it in general. So if it's very general, then you can't do anything. So in high dimensions, you want to impose some model, some structure. Otherwise, because of this phenomenon, it's impossible to do. Okay. There's one more thing that I want to do before we go to like the fun stuff, and that's sort of the ROC. Let's see. Maybe already like, I have like 1 or 2 minutes left. So how many people know what the ROC is? Oh, no one knows here. Okay. So we were looking at the accuracy, right, as a measure of performance on this classification rate. ROC is very common in practice, and it's a very useful picture of the performance of classifier. This is actually useful in practice if you understand what it is. And you can do it called receiver operating characteristic whenever you have a family of classifiers. So all these partitioning estimators, the Nadaria, Watson, they give you a family of classifier, even if you fix the bandwidth, because there is a threshold. So going back to the classification, so this is something like classification. If I have a classifier that is basically thresholding the regression estimate of the regression function, as I vary the threshold, I get different classifiers. We've seen that you need to change, like to take the threshold to be 1/2, like for the optimal rule, sort of. But let's say if you change your cost function, you've seen you get a different threshold. So the question is that if I vary the threshold, how can I trade off the 2 types of error? There are 2 types of error, true positive and false positive. And the ROC tells you exactly how you can trade off these 2 errors as you vary your calc. And basically what it is, I don't know why I don't have this stuff here, but basically what it is so ROC. So your classifier, let's say, is, I'm going to write it as, there is a parameter tau here. So your classifier is going to be indicator eta hat bigger than tau. So it's the probability that y hat is equal to y, given that y is equal to y. This is called the false positive rate, the true positive rate. and that the probability that this is 1 if y is equal to 0, this is called the false positive rate. So you take any generic x here, so you have a generic x and y. So you classify this x. For different tau, you classify it differently, but this would be a random variable here, depending on tau. The probability, you can ignore the tau here for now. Just fix tau. This is your classifier. The probability that y hat is equal to y if y was 1. This conditional probability is true positive rate. So your class was 1 and you correctly predicted it. Here, your class was truly 0. You predicted it as 1, and so this would be the false positive rate because it's doing it, declaring it wrongly, false positive rate. So if I vary the threshold, these numbers would depend on tau. So if I plot FPR, false positive rate as a function of tau, and true positive rate as a function of tau, and for different tau, I get different points here. And if you connect them, that would be the ROC. Okay, so that tells you at exactly this given false positive rate, how much true positive rate you would have. And so like a good classifier would be something that jumps here. Like if you allow for a little bit of false positive, then you can increase your true positive rate. The ideal classifier would jump would be this. And then by plotting these ROCs, you can compare the classifiers across the entire range of their FPR and PPR. So next time I'm going to come back, go over this a little bit more, and then move on to logistic regression and hopefully some more fun stuff and deep learning methods and stuff like that. Thank you guys.
Just a quick question for the cursor dimension. So you're right here. So you're saying the higher dimension will give the
when the dimension is higher. So let me just stop this. Well, the curse of dimensionality says your